Have you ever agonized over explaining the following to other people or even to yourself? The negative of negative 2 is 2, or minus 1 times minus 1 is 1. We'll answer these questions by taking a somewhat abstract but rigorous approach. We'll try not to be wishy-washy, and we'll focus on the integers. First, we have to take some care in understanding what negation is. To avoid confusion, we'll use neg of A to denote the negation of A. And you can think of neg as a unary operation having the following property. For every number A, neg of A is a number such that neg of A plus A equals A plus neg of A equal to 0. Now we're going to let S to be the set of numbers containing the natural numbers, the number 0, and the negation of the natural numbers. So from what we knew before, S is a set of integers, but we don't have to know that right now. For us, S is just this set of numbers. And the question we are going to ask is S closed under negation, addition, and multiplication? Actually, we don't quite know that yet, because given what we have defined, we don't really know that the negation of A is A. And there are other number of things that we normally take for granted that we haven't established. So what we're going to do is, we're going to play safe and look at the closure of S under these operations. So we're going to let T be the smallest set containing S that is closed under these three operations. Alright? Then what will happen is T will contain some funny looking elements. The negation of the negation of the negation of 4, the negation of 2 plus the negation of 5 plus 3, the negation of 2 plus 6 times 1 plus the negation of 3. Now these things don't look remotely close to the set of integers that we are used to. In fact, we hope that everything looks like what we have in S. What that means is we need some rewrite rules that are actually valid that will allow us to simplify these expressions. But before we figure out what these rules are, we need to make a few assumptions. Obviously, we want T to satisfy the usual rules of arithmetic. For example, if you have two numbers A and B, A plus B is equal to B plus A. If you have three numbers A, B, and C, adding B and C first and then A is the same as adding A and B first and then C. And if we have three numbers A, B, and C, A times the sum of B plus C is the same as A times B plus A times C. And the property of 0 holds for every element A. A times C is equal to B times A. And multiplying B and C first and then by A is the same as multiplying A and B first and then by C. And multiplying any number by 1 gives you that same number. And for each element A in T, A plus the negation of A is equal to the negation of A plus A, and that's equal to 0. There's a technical term for these rules, and the term is called axiom. So each of these is an axiom for arithmetic. Axioms are things that we take for granted without having to prove them. Now with these axioms, we can prove that the negation of A is equal to A. First, I'm going to label these rules. So the proof is as follows. A can be written as A plus 0, and the reason is because of A3. Now, 0 can be written as the negation of A plus the negation of A. That's because of rho n. Because negation of A is an element in T. And the rule says if you take an element and its negation, add them, you get 0. So this whole thing here is 0. Now, I can rewrite this as A plus the negation of A, and then add negation of the negation of A. And this is because of rule A2, right? Because I can change the order in which the additions are performed. Now, A plus negation of A by rule n is 0. So I have 0 plus the negation of A, and that is by rule n as well. And 0 plus whatever gives you that whatever. That's by A3. So this is exactly what we wanted to prove, right? We wanted to prove that A is the same as the negation of A. So using these axioms, I have derived this fact that the negation of A is A. So anytime you see two nested negations, you can get rid of them. The next thing we're going to prove is that 0 times any element is also 0. Why do we need to prove this? Well, for a very simple reason. It's not listed in any one of these rules. And it's not clear that this is even true. Intuitively, it should be, but remember that we are allowed to only make these assumptions down here. So we need to prove this. And the proof is not that difficult either. So we'll start with 0 times A. I'm using this symbol instead of the dot to make things a bit more clear. So 0 times A is going to be the same as 0 plus 0 times A, because 0 plus any element by rule A3 is the same as that element. Now, I can write 0 as the negation of 0 times A plus 0 times A, and that's by rho n. And then we have plus 0 times A, and using A2 I can rewrite this as the negation of 0 times A plus 0 times A plus 0 times A. We obtain this by applying rho m1 to all the 0 times A, and this is just the negation of A times 0 plus by rule d1 A times 0 plus 0. But now by A3, 0 plus 0 is again 0, so I can rewrite this as simply A times 0. But here I have negation of A times 0 plus A times 0, which is 0 by rule n. So we have established that 0 times A is equal to 0, again by assuming only these axioms. Alright, now we are going to tackle the problem of the negation of a number times a negation of a number. So what is the negation of A times negation of B? Well, the answer is that it should be A times B, and the proof is as follows. So I'm going to do most of this in place. So I'm going to start with the right hand side. So A times B is the same as A times B plus 0, and that's by rule A3. But 0 is the same as the negation of A times 0. This is obtained by what we have just proved and the rule m1. Now I can write the 0 as B plus the negation of B, and using d1 we get the following. Alright, and then applying A2, we can rewrite this as this. And now applying m1 to these two terms here, I get, and applying d1, I can rewrite this as, and applying n to this, we get 0 here. Now B times 0 is the same as 0 times B by m1. But we have shown before that 0 times whatever is 0, so this is actually 0. And now with this, we can conclude that this is simply negation of A times negation of B, because 0 added to anything is that thing by rule A3. So that's it. We have proved that the negation of A times the negation of B is the same as A times B. So no more agonizing over coming up with an intuitive explanation for this. It's an inevitable conclusion from these axioms, provided that you accept all the axioms that we have stated here. Now you might be asking, what if somebody refuses to accept one or more of these rules? And this is where dissension can come in. There are times when mathematicians do not all agree on the same working assumptions, thus resulting in different versions of theories. And they might even argue over the merits of the various theories. So opinions do exist in mathematics. One final note. How would one come up with these proofs here? Well, the short answer is with some work, experience, and insight. But the more general question of writing proofs will be addressed in a separate video.